So here are the climate projections. Temperature. Okay. On the left side are distributions of the mean surface temperature, okay, and how they look like, how they are distributed if you have on the very left side a 1.5 degrees Celsius global warming. Okay? So have a look at that distribution. Have a look at the distribution. This is on average 1.5 degrees Celsius, and here's a color bar where you can see the changes, but you can see it's not everywhere the same. You have some regions where there are only little changes in temperature, like over the Southern Ocean. And you can see there are changes which are significantly higher in the Northern Hemisphere polar, subpolar regions. Okay, you get these. And here you get changes all up to 2.5 degrees, maybe 3 degrees, something like that in these ranges. So if you now have an average of 2 degrees Celsius, as shown here in the middle, okay, again you get a similar structure, but it's more intensified. Okay? More intensified in the Northern Hemisphere and the polar, subpolar regions of the Northern Hemisphere. If you have a simulated change of 4 degrees global warming, shown here on the right-hand side, you get a much amplified signal in the polar, subpolar regions, including the mid-latitudes in the Northern Hemisphere. Okay, even more over land as opposed to the ocean region. And you get changes exceeding 7 degrees Celsius in these areas. Yeah? And here on the top right, it shows the projections of temperature changes by the end of the century, okay, based on which emission scenario has been used in the climate model. And you can see that the ones which the largest number here, this is the 8.5 scenarios. It means continued increase in greenhouse gas emissions by the end of the century actually gives you that temperature, global average temperature, more than 4 degrees. Also the 7 goes pretty similar. Okay. So if you manage to reduce the emission radically in the 1.9 or 2.6 scenarios. 1.9 means reduction to 0 by 2050. Okay. The 2.6 scenario means reduction to 0 by something around 25 years later. You actually end up with a temperature change of between 1 and 2 degrees. Okay. And you end up with scenarios that are shown here on the left side. Okay, so and this is now the choice. Okay, or this is the consequence of continuing to increase or stopping it. So this is as simple as it gets in terms of choices. Okay, which way do you want to? I mean, the other question is whether it's possible to do these rapid changes, but this is just scientifically, this is what you get. Okay. Alrighty, and here's also some attribution studies. You can look in these models, and again, you can see here are the results for low emission scenarios on the left, high emission on the right, and then you can see what contribution do the greenhouse gases make to the total change. Okay, and just you can see in each of these graphs, on the left side is the total temperature change, and then you can see that CO2 makes the biggest contribution, in any of these cases, followed by other greenhouse gases. And aerosols are usually you get the albedo effect dominates the aerosols response. You get a little bit of a cooling effect. Okay, but that's the old story. I mean, this is just the classical greenhouse effect. If you enhance the greenhouse effect, you get a warming. Okay, but it's really dramatic changes in northern polar, subpolar regions. Okay, that's what I mean. Let's have a go back. Let's see. Where's Australia? What do we get in Australia? Okay, Australia, we get something here. Let's have a look at under the 4 degrees Celsius change. You get something like maybe 4 degrees. That's the average change. But hang on, it's actually not just 4 degrees warmer throughout the year. You know, these temperature changes come in the form of heat waves. And we know that from observations. You know, over the summer you get these extreme heat waves. So you might actually get, or you will actually get, heat waves which are above 50 degrees Celsius. And you might get many of them. And that's really the concerning. So you really have to think about average. What does it mean? So here from this graph you learn that the projected average actually is not the same throughout the world. There are regions where you get an amplified response, in particular on land and in the northern hemisphere. Plus, imagine that this warming effect comes in form of an increase of the number and magnitude of heat waves. Alrighty. All right, again, climate projection temperatures is one more slide. Okay. And this is about CO2 emissions and how much the ocean and the land have taken up or take up from these anthropogenic emissions. Okay, these are projections. We're looking into the future. So, for example, here, if in this low emission scenario, okay, which is also color coded, by the way, you know, you have that blue color. Okay, these are the low emission scenarios where humans manage to stop greenhouse gas emissions within the next 30 to 50 years. And here you can see that the atmosphere and the ocean and land take up equal fractions of the CO2 emitted. Okay, and the rest remains in the atmosphere. And in the atmosphere, it actually causes the greenhouse effect. Okay? So now what happens if you emit more CO2 into the atmosphere? So what's shown in this graph for the high emission scenarios, it's actually the oceans and land also take up CO2, but at a lower fraction. So there is relatively more CO2 ending up remaining in the atmosphere. Okay? And this explains why you get more heating effect for this high emission scenarios. Okay, because the ocean and the land is a CO2 sink, but the sink effect becomes smaller. And this is another concerning effect, and that's why you get these extremely high warming effects, you know, once you go into the high emission scenarios. Okay, that's definitely something to think about. So now what you find in the IPCC report is you can compare the projections, which is shown here on the right. Okay, and this is shown for CO2. It's the top level, and temperature, which is the bottom level. You can compare this with reconstruction of CO2 concentrations and temperatures over the last 60 million years. Okay, and this is what's shown here. Okay, so if you look at that high emission scenario, the 8.5 scenario up here, you actually come to a situation which resembles the hothouse climate that you had in the early Eocene. Okay. And that's extremely concerning. We're talking about changes in the past 300 years with something, which occurred on much, much longer time scales. Okay, so high emission scenarios will create a hothouse climate on Earth not experienced in over 50 million years. All right. Temperature, that's the temperature. So precipitation. What do the models predict? And this again is shown here for different scenarios which are expressed as the average warming. Okay, for example, on the left side, this is an average warming of 1.5 degrees Celsius. Okay, this corresponds to the low emission scenarios. And then you can see the changes, the change in percent of precipitation. And if you look at these maps, you can see that there's some more precipitation in the intertropical convergence zone, and you see in the subtropical areas you get a reduction of the rainfall. So it's pretty much that wetter areas get wetter and drier areas get drier. Okay, but if you go to the high emission scenario again, you can see that there are significant effects here of intensified rainfall predicted for Northern Africa, for the Northern Africa region and the Asian region, but not here over China. You get that reduction. All right. So that's what the model predict, but indeed precipitation is always a little bit harder to predict, and you have to watch out for that and look at future observations. Relevant to this is also the soil color moisture change. Okay, this is really relevant here, and it's the link to the vegetation. Okay, you have a look at the pattern of the simulations, and you can see a decrease, okay, or an increase in soil color moisture. Okay, and you get areas where you get an increase, here shown in green. Okay, you could get significant increase, or you get areas where you get decrease. And decreases are predicted, for example, for the areas around the Mediterranean Sea, for northern parts of South America. You can see Australia in here too. Okay, and this is all highly relevant because it's linked to vegetation, to biomes, to ecosystems, and so. This is the link to the vegetation, the direct link to it. So the sea level predictions. Okay, and we are actually looking at longer time scales here, and we're looking at, because sea level change is a relatively slow process. Okay, and we're talking about maybe a meter. Okay, by the end of the century, but in the future, by the end of 2300, the year 2300, you get projections of 3 meters up to 7 meters for high emission scenarios. Plus, cannot be ruled out that ice sheet instability processes occur, which can lead to higher sea levels. And this is uncertain. Okay, it is a speculation, but it cannot be ruled out. So we're looking at significant sea level changes on a time scale of a few hundred years. which is not long. Okay, so that's the sea level projection. So Arctic sea ice and ocean pH, they both depend on the emission scenario. Okay. So we're looking at Arctic sea ice, and we observed a decrease, and that decrease will continue. Okay, for all scenarios. It will continue for all scenarios, but then there will be a difference. Either you still have ice in summer, or you will have a partially ice-free Arctic Ocean in summertime. And that depends on the emission scenario. Okay, you get two possibilities. The global ocean surface pH is going to decrease. It continues to decrease, but it also depends on the emission scenario. So it could stabilize at around 8 for the low emission scenarios, or it could further decrease. Okay, and lead to the under situation of certain areas of the world ocean, of the critical mineral of aragonite, which is essential for the formation of calcareous material. Okay, again, this one also links to, you can see how many features are linked to greenhouse gas emissions. So now let's, at the end of this lecture, just have a look at extreme events. Again, there are so many different types of extreme events. So what you find in that IPCC report is what they've done is actually they looked at different land and coastal areas. Okay, and then they looked at how likely is an increase of different types of extreme events. Okay. So for example, here at the top it shows mean surface temperatures. Okay, mean surface temperature, we're talking about mean surface temperature, the average surface temperatures. Okay, and regions with a high confidence level is given here in this purple. Okay. And you can see that all areas experiences a mean surface temperature increase. Again, that's a high confidence. If you have something with a medium confidence, it's shown in pink. Okay, and then you have also areas with a decrease, which is shown here in the darker orange and a lighter orange color. And then you can have a look at all different type of extreme events, like extreme heat events. And you can see that there is a high confidence of an increase. Cold spells, okay, get a decrease. Also a high confidence of a decrease. You have frost events, and you can look through these river floods, and you can see that there is an increase of these extreme events. Fire weather, okay. So these changes refer to around 2050, mid of this century, consistent with the 2 degrees Celsius global warming, compared to a similar period, something like 50 years ago, or something around that. Okay, and what you can see, increases in extreme heat events, fire weather, increases in heavy precipitation and floods. It doesn't tell you how much, but you get that confidence that there will be increases. And the list goes on. So the list is going on here let's have a look here. Go one back again, sorry. This is now separated into heat and cold events, wet and dry events. Okay, you can see events linked to temperature, events linked to precipitation or droughts. Okay. Have a look at these events which are related to wind events. Okay, mean wind speed, unclear. Okay, severe windstorm, that's also unclear. Tropical cyclones, We don't know. There's no real evidence. And so, but if you look at now snow and ice, as shown here, okay, decrease in snow, glacier, and ice sheet, we have a high confidence in many regions. Permafrost decrease, yes. Lake, river, and sea ice, yes, and so on. Okay, and then you can go down. There is, in terms of other effects, what's also included here is atmospheric CO2 at the surface, the increase. It's not really an extreme event, but anyway, they included it. So that's all possible increases in extreme wind events and a high confidence in many regions. Okay. There's even more. I almost forgot about that. Coastal, relative sea level, high confidence of an increase. Coastal flood, high confidence in an increase. Coastal erosion, high confidence. Marine heat wave, high confidence. Ocean acidity, high confidence. Okay. And in the open ocean also some features. That's about ocean acidification, dissolved oxygen levels, marine heat waves, marine ocean, mean ocean temperature. Sorry about that. Okay, so study questions. What are emission scenarios? So your neighbor comes knocking. Hey, what are these emission scenarios that they're always talking about? I don't understand it. So how will the water cycle change according to climate projections? How will surface temperatures change according to climate projections? Which regions are most affected by climate change? Why are temperature changes generally greater over land than over the sea? Why will the temperature of polar regions increase dramatically? Which type of extreme events will increase in the future? So, thanks for watching.